Hello friends, I welcome you in lecture number 53 on Laplace transform. In lecture number 52, we have discussed how we can obtain inverse Laplace transform using second shifting theorem. In this lecture also we will discuss some more problems on finding inverse Laplace transform using second shifting theorem. So first we recall the inverse Laplace transform for inverse Laplace transform using second shifting theorem. So we know that suppose L inverse of capital F of S is small f of t, then if we are interested in the inverse Laplace transform of e raised to minus as times capital F of S, then this is given by unit step function at point A into value of this function at t minus a. So whenever we want to obtain inverse Laplace transform of a function which is multiplied with e raised to minus as, then first we will obtain inverse Laplace transform of capital F of S, and this inverse Laplace transform is given by unit step function at point A times value of this function at point t minus a. So we consider first this function e raised to minus 2s divided by s minus 5, and if we compare with e raised to minus as, we have a equal to 2 and f of s is 1 divided by s minus 5, and we know that L inverse of 1 divided by s minus 5 is e raised to 5t, and this we denote by small f. And now we can directly write down by second shifting theorem. Now we don't have to use that notations that this is capital F of S and so on. So by second shifting theorem, L inverse of e raised to minus 2s divided by s minus 5, this is equal to value of function f at t minus 2 multiplied with unit step function at t minus 2. F of t is e raised to 5t, and therefore f of t minus 2 will be e raised to 5 times t minus 2 into u of t minus 2. And if we wish, we can rewrite this as e raised to 5t minus 5 into 2, 10 into u of t minus 2. So this is very easy. Here we have instead of, if we compare with e raised to minus as, value of a is a itself, so unit step function will be at point A, and we have to first decide what is L inverse of 1 over s cube, which is multiplied with e raised to minus as, and we know that this is given by t raised to 3 minus 1 divided by 3 minus 1, that is 2 factorial, and this is t square divided by 2. Recall this formula. If we have L inverse of 1 divided by s raised to n, then this is given by t raised to n minus 1 divided by n minus 1 factorial if n is a natural number. So here we have used this formula for n equal to 3. So we have 3 minus 1, that is t square divided by 2 factorial, and this is our small f. And now we can write by second shifting theorem. We should at least mention one time that we are using this result second shifting theorem. By second shifting theorem, L inverse of e raised to minus as divided by s cube equal to value of function f at point t minus a multiplied with unit step function at point A. F of t is t square by 2, and here we have to replace t by t minus a, so this is square of t minus a divided by 2 times unit step function at point A. So we consider another example. here function is 1 plus e raised to minus pi by 2 times s divided by s square plus 4. So this we can rewrite as 1 divided by s square plus 4 into e raised to minus pi by 2 into s divided by s square plus 4. So L inverse of this function will be equal to L inverse of this plus L inverse of this. Now this is ready-made formula. L inverse of 1 divided by s square plus 4 is sin 2t divided by 2. But this is multiplied with e raised to minus pi by 2s. So first we have to decide inverse Laplace transform of this function. So for that, first we write down L inverse of 1 divided by s square plus 4. This is equal to sin 2t divided by 2, and this we call as say f of t. And here we have e raised to minus pi by 2 into s is multiplied with this. So therefore by second shifting theorem, inverse Laplace transform of e raised to minus pi by 2 times s divided by s square plus 4, this is equal to unit step function at point pi by 2 into value of function at t minus pi by 2, value of f at t minus pi by 2, and this is our f. Here we replace t by t minus pi by 2, and this 1 by 2 we write in the product, and here we replace t by t minus pi by 2, and this multiplied with unit step function at point pi by 2. Now this we can simplify, we can multiply by 2. So this is sin 2 times t minus 2 into pi by 2, that is pi, into unit step function at point pi by 2. And sine function is odd function, so if we rewrite this as minus of pi minus 2t, we will have negative sign outside. So this is equal to minus sine of pi minus 2t times u of t minus pi by 2, and this we can again rewrite as pi minus 2t means in second quadrant. In second quadrant sine is positive, therefore this is going to be sine 2t and u of t minus pi by 2 in the product. So this is inverse Laplace transform of e raised to minus pi s by 2 divided by s square plus 4, and our function is this function plus this function. So now we write down inverse Laplace transform of given function. Inverse Laplace transform of 1 plus e raised to minus pi by 2 into s divided by s square plus 4, this is equal to L inverse of 1 divided by s square plus 4 plus L inverse of e raised to minus pi by 2 into s divided by s square plus 4, and this is by linearity property for inverse Laplace transform. Now this is equal to sin 2t divided by 2, and this is minus 1 by 2 sin 2t unit step function at t minus pi by 2, and if we wish we can consider this sin 2t by 2 as common. It is present in both the terms, and here we can write this is 1 minus unit step function at t minus pi by 2. So this is very easy, but you must be careful. Here we have to apply unit step function to obtain inverse Laplace transform of this function only. For this it is ready-made formula. This inverse Laplace transform is sin 2t by 2. So you can easily do this type of problems using second shifting theorem. And if you wish, you can try this as your homework, and you can compare with e raised to minus as. So a equal to 3, and your capital F of s is 1 divided by square of s plus 2. So first obtain L inverse of this function and denote it by small f of t, and by second shifting theorem L inverse of this function will be equal to f of t minus 3 multiplied by unit step function at point 3. So remember this important result and apply this result whenever you have question like this. Obtain inverse Laplace transform of e raised to minus as times f of s. So if e raised to minus as is in the product, then to obtain inverse Laplace transform you have to apply this second shifting theorem. There is no other method to obtain the inverse Laplace transform of this type of functions in your course. So you must have to apply second shifting theorem whenever you are given a function in which e raised to minus as is in the product. So for that, first obtain inverse Laplace transform of a function which is in the product, and then replace t by t minus a in that function and multiply it with unit step function at point A. So this is all about this session. I hope you like it. Thanks for watching.